Algebra 2, Part 2, Section 2.6. So I started talking about a piecewise function, and this is the piecewise function we had. We know that it's going to be broken up into pieces. So for part of our graph x plus 1, this red portion, we only want the graph of x plus 1 as long as x is greater than 0. So I'm going to come over here with my white pen, and I'm going to just erase the part that I don't want. I don't want any of these values for when x is less than 0, is less than 0. So I don't want that. I don't even want when it's equal to 0, actually. So I'm going to be extra and change this to an open circle right here, because this value of x being f of x being x plus 1 cannot exist when x is 0. When x is 0, I want these values here. When x is 0 or less than, I want these values. So here, all here is where x is 0 or less than 0. So I don't want, now go back to this graph, I don't want any of this part of the graph. I don't want when x is greater than 0. I want when x is equal to 0 or less than 0. And so this part of the graph is what I want. So this graph that I'm asking for, this piecewise function, is going to be made up of little broken pieces of other graphs. And in this case, they gave us that it should be made up of this part and this part. So what I'm going to do is I'm actually going to put these two graphs together. So voila, we get this. I took this red part of the function, put it here, and this purple part and put it here, and this is a piecewise function. So you can see two different things going on, but they all come together to make one function or one graph, okay? So a piecewise function can have 2 pieces, 3 pieces, 4 pieces. The things you need to keep in mind is the domain of each of the pieces. And so this purple piece has a domain that's x less than or equal to 0. This red piece has a domain that is x greater than 0. And so that's why we have it like this. So just a quick recap. The step function is going to be a function that has different layers or different steps in it. And those steps oftentimes refer to payment or cost. And the example we did was cost and hours in a parking lot. A greatest integer function is a type of step function, but it's the one that I refer to as the birthday function. And it is written as y is equal to this double bracket x, double bracket x. Sometimes it's called a floor function. And it has kind of a specific open circle, closed circle kind of situation. All of them have open circle, closed circles when you're dealing with a step function, so I should probably righteously do this. But sometimes, depending on the situation where the open and closed circle will be, you need to check that out. A constant function we know is y is equal to some value b. Of course, we know that could also be written as f of x is equal to some value b. And that's going to be a function where we know that the graph is going to be a horizontal line going from left to right through some point b. And our next function is the identity function, and it's like looking in the mirror. If x is this, y is the same thing. If y is this, then x is the same thing. And this function is this gorgeous diagonal that goes straight through the origin. That's not too gorgeous, it's a little bent, but you get the idea. Our absolute value function will always have a v shape. Our absolute value of a linear equation, I should say, I'll be a little bit complicated here, will always have a V shape. Sometimes these V's can be lower, let's try to make it a V, can be lower or upside down or narrower or even wider, okay? So we're looking for a V shape when we're thinking about absolute value, and our piecewise function is given as f of x is equal to, and we get a curly bracket, in a sense a set of rules, like blah, 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 if x is this, if x is that, and there's always like an if, and this information is usually domain information. So you might be if x is greater than, if x is greater than 2, if x is somewhere between, I don't know, -2 and 2, and if x is less than -2, less than or equal to -2. So you could have something like this, and you have different things going on, and your graph depending, would be broken up similar to the domain here. So it looks like -2 and 2 are the breaking points. So I might have one graph that does this, goes out there, one graph that does this in here, and another graph that does this. So you can literally have 3 pieces of things happening when you have a piecewise function. And let's get started on some examples. So in this case, we're already given the fact by the title that we're dealing with a step function. Labor costs at Fix-It Auto Shop are $60 per hour or any fraction thereof. Draw a graph that represents the situation. Now, that or any fraction thereof implies to me, and I think to most people, that if you go over that hour, then you get another $60. So the moment you go over, you're already up. You're paying for the next hour of labor. So let's go ahead and make our graph. Let our hours be down here, and our cost be along the side. And let's label it. So I've labeled this 1, 2, 3, 4, all the way up to 10 hours, and I've labeled this in multiples of 60 because that's how I'm being charged. So for the first hour, up until that hour, I'm going to be charged $60. So as soon as I bring it in, even if it's a 15-minute repair job, they're going to charge me $60. Up until all the way up, if I don't bring it in, obviously I'm not charged anything, so that would be down here. But if I bring it in, and it spends a minute at the shop or a second or any time, they're going to charge me some labor up to 1 hour. And as soon as I go over that hour, boom, I'm being charged $120. And as soon as I get up to 2 hours, boom, I'm going to be charged over 2 hours. I'm going to be charged for 3 hours, and so forth and so on. Look at how these dots are a little bit different in terms of the way they play out than the birthday function or the greatest integer function we talked about. And then so we can see that this is the pattern that we have. So here we have an open circle and a closed circle over here. Oops, I got excited. Here we have an open circle first, then a closed circle, but with the greatest integer function, it was the opposite way. Think about why that would be. And so we go all the way up here in terms of labor per cost, okay? So if it costs, if somebody was fixing my car and at Fix-It, a great Fix-It Auto Mechanic or whatever the thing's called, if it took them 4.5 hours to work on the car, I would be paying 4 times the cost, but plus another $60, because I'm going to pay for 5 hours of labor, because as soon as I get past the 4, I'm in the 5th hour of labor. So 5 times 60 is going to give me that 300, even if I'm here with slightly less or much less than 5 hours. But as soon as I go over the 4 hours, that's what happens. All right, constant function, graph this bad boy. Well, this is easy cheesy for breezy because we talk so much about it. This is just like y is equal to 3. We know it's a horizontal line. Point here, da 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 da. Too easy. Give me a hard one. All right, so this one wasn't hard at all. What was I going to say? Yeah, this isn't hard at all. I'm not even going to over-explain it. All right, let's look at the next example. Example is an absolute value function. So we've got 2. We're going to graph this one and this one. F of x is equal to the absolute value of x plus 1, and g of x is equal to the absolute value of x minus 2. Let's check it out. So the fact that this is an absolute value function, or these are absolute value functions that we're going to graph, I'm thinking about the example we did earlier. Y is equal to the absolute value of x came out to be a v. So these we should expect to have a v situation as well. We can do an xy chart if we'd like. There's also another way, and we'll talk about it. I'm going to do the xy chart, but we'll talk about what this should be. Since y equals absolute value of x, this we didn't talk about exactly is a parent function. I think we're going to talk about it later. This is a parent function, meaning this is like the generalization, and these are kind of like takeoffs from it. So this plus 1 actually tells me it's going to end up being up 1. This minus 2 tells me that this graph will be down 2, but pretty much the same. And we'll see how that plays out when we do an xy chart. So as usual, if I'm going to make an xy chart or an f of x chart, I'm going to plug in some values for x, and I just chose these kind of randomly. We'll talk about how to choose them a little bit better than random. And so I put a -2 in. -2 becomes a +2. This answer becomes a 3. -1 in. -1 goes in. It becomes a +1. This is 2. 0 in. This is a 1. 1 in. This is a 2. 2 in. This is a 3. 3 in that equation, this is a 4. And what you want to see when you're looking for, when you're doing a table for one of these guys, you want to see this bend, 3, 2, 1, 2, 3, 4. You want to see it go down then come up because that's going to show me the bend. So I'm going to plot these points really quickly. At -2, I'm at 3, boom. At -1, I'm at 2. At 0, at, starting to have some trouble. All right, graph, be my friend. So I plotted my points, and I see that this will continue out in this direction, and this will continue out in this direction, and there's my v, just as we said, up 1. Let's do the same thing for g of x function. I've chosen some of the same values, and when I plug it into the equation, if I plug a -2 in here, I get 2 minus 2, which is 0. If I plug a -1 in here, I get 1 minus 2, which is -1. If I plug a 0 in there, 0 minus that is a -2. Plug a 1 in, I get a -1. Plug a 2 in, I get a 0. And plug a 3 in, I get a 1. So I'm going to graph these values. I might have to pause for a second to do that, but I'm at -2, 0, -1, -1, 0, -2, 2, I'm sorry, yeah, 0, -2, 1, -1, 2, let's get 2, 1, -1, there it is. At +2, I get 0, and at +3, I get 1. So you see, here's this v again, but now it's sliding down, all right? So it's the same graph, but it's shifted up and down, and we'll talk a little bit more about how to calculate those things, all right? So that's how I graph those. Let's look at our next example. So I'm going to highlight each of these different. Okay, so I started doing crazy stuff. Let me just pause you for a second. Okay, so your graph is going to start, when you have a piecewise function that you need to graph, it's going to start off like this. And so what we'll do is, for our intents and purposes, we want to kind of separate them. So I'm going to say this one I'm going to call my orange function, and this one down here I'll call my blue function. So if this orange function is my orange function, then typically what I'm thinking about is part of the graph I'm going to graph is f of x is equal to x minus 4. And then another part of the graph I'm going to graph as f of x is equal to 1, which is a constant function. And to determine where I'm going to do that, I use this information right here. It says graph this, x minus 4, if x is less than 2. So if x is less than 2, here's where x is 2. If x is less than 2, that's going to be everything behind that mark. So I'm going to actually shade that in. So everything here and back should be this orange function. I'm a little sloppy with this, but you get the idea. So I'm going to call this the orange zone, because the orange zone is all about things, all x values that are less than 2. Whereas the blue zone, which I'm going to have to color on this side, is everything that is equal to 2. So I'm going to make sure and make my line blue here, because it's equal to 2. So it owns that 2 zone. Or greater than 2. And I know my shading is a little sloppy, but stay with me. Or greater than 2. So I want the blue function only graphed on this side. And so now the blue function is easy, so I'm going to start off with that one. My blue function is f of x is equal to 1, which we know is I'm listening, constant function. Very good. And so that means we would start here and draw a line straight across, but I only want it in the blue zone. So this is, this is 1. And I would draw a horizontal line here, but I'm only going to draw it from here, solid dot, because I'm including 2, all the way out forever and a day. And this guy over here needs to the orange one is going to be where y or f of x is equal to x minus 4. So I can choose values and plug it in here to make myself happy. So I can say, well, if I do x, y, well, actually I can do the point slope thing. I can do a slope intercept kind of form thing and see how that goes. So if this is already in slope intercept form, my y-intercept is -4, 1, 2, 3, 4. So that's a point. And then my slope is 1, so it's up 1 over 1, up 1 over 1, but I have to put an open circle here, and this is going to continue down. I could have also done this with using points using a table, but I was trying to be fast, realizing our time is running out. And so this is the graph that I get. All right? Sorry for not putting your assignment in the beginning. It's pages 93 to 94, 15 through 44 all. Let's talk